Okay, welcome back to the last part of limits. So this is a very specific type of limit, but I wanted to give it its own video just because this is kind of a messy kind of topic, seems to have a lot of confusion for people. And so I thought just a separate video would kind of help us out here. It's called a limit of a composite. So first off, what's a composite? A composite is when you're plugging something into something. So f of g of x, or you could say like f of g of 2, or it's some kind of composite situation involving a limit. All right, so if we have a limit, and the way I have it situated here as x approaches a is whatever number that you're talking about, then it's equivalent to, and now let's read this notation, f of the result of the limit as x approaches a, this f shouldn't be here, sorry, of the interior function. So let me translate that for you in English because I know I just edited that on the fly here. Hold on. So it's the interior piece, this g of x, the limit of the interior piece plugged into f. So again, as I pre-warned you, this is kind of messy, the notation. So let's think about this for a second. If I tell you, just to have an idea of what we're talking about, if I tell you, you know, f of 2, that means we want to plug 2 into f. So for example, if f of x is equal to x to the third, f of 2 just means we're going to plug 2 into that. That gives us 8, so 2 to the third. What we were just saying a second ago is that if you have the limit as x, we'll go with approaches 1 for f of g of x. That is going to be equal to the limit as x approaches 1 for the interior function, and then it's f of that result. So in other words, whatever this result is, it would get plugged into f. Now, there's one little rule with that. It's if f is continuous at that inner limit. Okay, now we haven't really talked about continuous or continuity yet, but in other words, it's going to mean continuous, think of it as connected, or there's no holes in the graph, there's no skips or jumps in the graph. So I have a series of problems laid out here because I realize this is kind of confusing at first glance. So I think our best bet is to just look at these problems and go through one by one. Okay, so that said, feel free to pause this video if you want to copy these graphs down or you want to wrap your head around what the problem's asking you. But it says the limit as x approaches 0, and here is our composite limit. So that's going to be equal to f of, and then the limit as x approaches 0 for g of x. So let's check out what happens. As x approaches 0 on g of x, that result, hopefully that limit from the previous two videos, that makes sense to you to say that that limit would be 0. And then f of 0 means we come over to this graph of f, and f of 0 would be -1. So the result of that limit would be -1. Now, the key to this is f is continuous at the limit. So if this is continuous and it's connected, then you're good to go. Okay, so hopefully that makes sense. We will try a few more here. Okay, next one says, sorry, let's get this in the frame. Limit as x approaches 1 for g of f of x. So in this case, as we approach 1 on the inner function, so you can rewrite all of these if you want, or if you're just comfortable with it, that's fine. As we head to 1 on the inner function, that limit is 2. So the limit as x approaches 1 for f of x, and then it's going to be g of, right? Because we plug it into the outer function. So this limit, as we approach 1, that limit is 2. But we've got an issue now. When you come over to g, this is not connected, right? So we don't have a clear-cut answer. Now there's a secondary rule. When we go back to this original graph, if both sides of the graph are underneath the value that it's approaching, let me say that again. if both sides are underneath, below the value it's approaching, it's equivalent to saying from the left. So as we approach it from 2 from the left, this is going to give us a result of 1. If both sides are underneath, it's equivalent to from the left. So let's look at that all over again. We said the limit as x goes to 1 for the graph of f. We agree that that answer is 2. But when I come over to here, if this is not continuous and connected, then we need to analyze further. And if both parts of the graph are underneath where you approach, it's equivalent to saying you're approaching this value from the left. So as we approach 2 from the left, that answer is 1. Okay, obviously we should look at the counter of that example. So for the next one, the limit as x approaches 2, f of g of x. So this is going to be f of the limit as x approaches to g of x. Okay, so as we head to look at g over here, as we approach 2 on the graph of g, hopefully everybody's on board that that limit result is 1. Okay, when we come over to here, f of 1, this is not continuous. It is not connected. So same rules apply. Now this time, though, if everything is above where you're approaching, that's equivalent to saying from the right. And from the right, that would give you an answer of 2. So again, everything below is considered from the left. Everything above is considered from the right. And now that's only if, when you go to the secondary part of the limit, that it's not continuous. Because if it's continuous, well, then you're going to get the same answer either way. It doesn't really matter left or right. So this isn't important anymore. The example 2 and 3 is only if, when you head to the secondary part of the problem, if it's not connected, then that shows you how you can come up with your solution. Okay. Let's take a look at example 4. Okay, so now this is f of x. It's the same graph used twice, but it's still the same idea. So this is going to be f of the limit as x approaches -2 f of x. Okay, so the limit as we approach -2, and this is the graph of f, this whole graph. The limit as we approach -2, that answer is 1. And then f of 1, we go look over here, but it's not connected, it's not continuous. But what was the original story? These were both from above. And if it's both from above, then we can say that's the same thing as from the right. So as we approach this from the right, that's going to give us an answer of 1. Okay, let's look at number 5. So same idea, different graph. As we approach -1, so this is going to be in here. As we approach -1, that result is 3. So then when you head over to 3, same deal. There's a jump or a skip. It's not continuous. These were both below. Both below means from the left. And as we approach 3 from the left, that result is -2. All right, let's check out number 6. So we have the limit as x approaches -2 for f of g of x. So when we go to that inner piece, as we approach -2 on g, no problem. The limit as we approach -2 is -2. When we go to the other part, though, it does not meet. It's not continuous. So we go back over to here. Now, what's different in this example? This is not entirely above or entirely below. So like, in other words, if this whole graph was above, it was from the right. If this whole graph is below, it's from the left. And in this condition, or in this circumstance, if you have one of each and it's not specifically, you can't tell, then the answer is D and E, and that is does not exist. Okay. So for examples 1, 2, 3, 4, 5, 6, I think hopefully with a little bit of practice, those ones will become very, very straightforward to you. I think 7 and 8 is a little more confusing, and we might need to watch this a couple times to wrap our head around it. Let's dive in and see what we got here. So what's different here is the limit as x approaches -2. When you do this interior function, it's already there's no agreement, right? So all the other ones we did, when you did the interior piece, you came up with some kind of answer. Okay, so I've seen some videos on the internet and elsewhere that tell you that this is immediately does not exist, and that is not correct. It's correct maybe for like 90% of problems, but there is a situation here where you can, in fact, come up with an answer. So let's review that. If the interior piece does not exist, we still want to check the limit from the left and right on it. So as I approach -2 from the left, that answer is -1. And as I approach -2 from the right, it's -2. Okay, you then want to go to the second graph. And as I approach -1, the answer is -1. As I approach -2, the answer is -3. If these two things were to be in agreement, or this, in other words, the same number, you would still have an answer to the question. They do not in this case, but if these two things were in alignment and those limits matched, that would be the overall limit to this graph. Let me show you, obviously, the example where that happens. The last one on this video is example 8. Limit as x approaches 2 for g of x. As we approach 2, on our interior limit, we don't have an answer, right? But as we approach 2 from the left, it is 3. And as we approach 2 from the right, it is 4. So we head over to the exterior, and now we can say 2 from the left was 3 and 2 from the right was 4. As we approach 3 and 4, these come up with the same value. And if that is the case, that is the overall limit to the composite function. All right, so 7 and 8 are most likely the ones that people tend to get confused with. But that being said, I think this video is worth watching a couple times to wrap your head around what we just discussed. Composite limits are a little less intuitive than some of the other ones, so I would advise you to watch this a couple times, try to make sense of it. As always, feel free to message with questions, and I will see you guys soon.